Welcome to the deep dive. You send us your sources, and we dig through them to pull out the core knowledge for you. Think of it as your shortcut to understanding what really matters.
Yeah, exactly. And today, we're diving into a shape you see everywhere, the cylinder. We've got some great learning materials here, definitions, those all-important formulas, and even some solved problems to look at.
All right. So our mission today is basically to get a really clear, engaging picture of cylinders, both the solid kind and the hollow ones, and understand how those formulas actually work without getting bogged down in too much detail.
Sounds good. Just the essentials.
Okay, so where do we start? What, defines a cylinder?
Well, the simplest way to think about it is it's a solid shape that has the same circle at both ends, and it's kind of straight between them. Uniform circular cross-section is the more technical term.
Like a tin can or maybe a log.
Exactly. That consistent circular slice is the key idea.
Okay, let's unpack this a bit more. So mathematically, what do we need to describe one?
Really, just two key things. First, the radius of that circle at the end, the distance from the center to the edge. We usually call that R.
R for radius, got it.
And second, how tall it is the height, which we call H.
Okay, R and H. Simple enough.
Right. And from just those two, R and H, we can figure out quite a lot using formulas. First up, the area of that circle at the end, the base, how much flat space it covers.
Yeah, I remember that one. It involves pi, right?
It does. The area is pi times the radius squared, or pi r.
Okay, pi r2 for the area of the base. And the distance around that circle, the perimeter.
Yeah, the perimeter or circumference. That's $2 R dollars.
$2, okay.
Now think about the sides, the curved part. Imagine, like you said, a tin can label. If you peel it off and lay it flat, what shape do you get?
A rectangle.
Exactly. And one side of that rectangle is just the height of the cylinder, H. The other side is the length that was wrapped around the circle.
Which is the circumference, the $2, 2R.
You got it. So the area of that label, the curved surface area of the cylinder, is just height times circumference. $2 H days.
Ah, okay. That actually makes a lot of sense when you think about it, like unrolling it. $2 ERH dollar.
So if you want the total surface area, you need that curved part plus the two flat circles at the top and bottom.
Right. So the $2 ARH plus two lots of the base area, 2 lot RHU plus 2 pil RHA.
Precisely. And sometimes people factor that, pull out the common terms to write it as $2 ERH plus R toller. It's the same thing, just looks a bit tighter.
$2 ARH plus R.
What's neat is seeing how they connect. The curved area uses the circumference uses the radius. It all links back.
And the last big one is volume, right? How much space it takes up or how much it holds.
The volume. And that's actually quite intuitive, I think. You take the area of the base, that R2N, you just multiply it by the height.
So DRHA base area times height.
That's it. 2 pi RHE, that's your volume for a solid cylinder.
Okay, so those are the key formulas for your standard, solid cylinder. But the material you sent over also talks about hollow ones.
Ah, yes. Hollow cylinders. Think pipes, tubes, paper towel rolls, that kind of thing.
Right. So what changes there?
Well, now you have two radiuses to think about. There's the radius to the outer edge, let's call that big R, and a radius to the inner edge, the hole, which we call small r. The height H is still the same.
Okay, big R and little r, outer and inner. And I guess the thickness of the wall is just the difference.
Exactly. The thickness is just draught orders.
Here's where it gets really interesting, I suppose. Calculating areas and volumes must be different now.
It is. Let's start with that cross-section again. If you slice through a pipe, you don't see a solid circle, you see a ring, right?
Yeah, it's like a donut shape.
Sort of, yeah.
Yeah.
And the area of that ring is the area of the big outer circle minus the area of the inner hole. So pi R2.
Makes sense. Take the big area, subtract the missing bit.
And again, you'll often see that factored as pi R2. Can be handy sometimes.
Okay. What about the surfaces? There's an outside surface and an inside one now.
That's right. You've got the external curved surface area, which uses the outer radius R. So that's $2 PRH.
$2 TRHR.
And you've got the internal curved surface area using the inner radius R, which is $2 PRH.
$2 and inside and outside curves.
So for the total surface area of a hollow cylinder, you need to add up, let's see, the outer curve, $2 P, the inner curve, $2, and the areas of the two ring-shaped ends we talked about.
Ah, right. So 2 lots of that pi RH area.
Exactly. So the whole thing is $2 PRH plus $2 plus 2 area. Looks a bit messy, but it's just adding all the bits. Outside wall, inside wall, top ring, bottom ring.
Got it. It's logical when you break it down.
Yeah.
And the volume, not the space inside, but the volume of the actual material making the pipe.
Good question. You find that by taking the volume of the whole cylinder as if it were solid, using the outer radius r, and then subtracting the volume of the empty space inside using the inner radius r.
So volume of the big cylinder minus volume of the hole.
Yep. Pi by RD.
By Aristo. Or, factored again, type error 2.
Or it's amazing how that little hole complicates things formula-wise.
Well, it reflects reality, right? If you're
Right.
making pipes, you need to know how much metal you're using, which is that volume of material. You also need to know how much water can flow through, which relates to the inner volume. So these formulas are super practical.
Absolutely. And speaking of practical, our source material has some work examples. Let's dive into the first one.
Okay.
It says we have a cylinder where the curved surface area is 4,400 square centimeters and the circumference of the base is 110 centimeters. We need to find the height and the volume.
All right. So we know curved surface area is $2 RHA, and that equals 4,400. We also know the circumference is $2 RHO, which equals 110.
Hang on. The $2 R dollar part is the circumference.
Exactly. So the curved surface area formula, $2 RHJ, is just circumference times h.
So $110 times h comes $3,400.
Right. Which means we can find h really easily. Just divide 4,400 by 110.
4,400 divided by 110. That's 40. So the height is 40 centimeters. Nice and easy. See how spotting the connection helped.
Definitely. Okay, now for the volume. We need the radius r for that using pi r2i, as we know $2 r equals 110.
So we can rearrange that to find r. If we use pi as a frac 7 thing, then $2 times frac 7 times r equals 110. A little bit of calculation there.
Let's see. 44 over 7 times r equals 110. So r is 110 times 7 divided by 44, which simplifies to 17.5 centimeters. Or 35.2.
Looks right. So now we have R is 17.5 centimeters, and we found H quad 40 centimeters. We just plug those into the volume formula, T pi R2L.
Okay, so frac 7 times 17.52x, $41. That sounds like a job for a calculator or careful multiplication. The example says it comes out to $38,500 cubic centimeters.
It does, 38,500 centimeter. What this shows is how knowing just a couple of properties like curved area and circumference lets you figure out everything else.
Yeah, that's cool. Okay, problem 2 is a bit different. It's about writing words with ink from a bottle using a fountain pen.
Ah, the practical application example.
Right. The pen barrel is a cylinder, 7 centimeters long, diameter 5 millimeters, so the radius is half of that, 2.5 millimeters or 0.25 centimeters.
Okay, R 0.25 centimeters, H is 7 centimeters.
And it says one full barrel holds enough ink to write 310 words. The ink bottle holds 1/5 of a liter. How many words can you write with the whole bottle?
Okay, step 1. Find the volume of ink in one barrel. That's just the volume of the cylinder. $280.
So, T times 0.25 times 7 is 7. Using on-proc fracs again, that calculation gives 1.375 cubic centimeters. A tiny amount.
Tiny, yes. But that small volume writes 310 words.
Right. And the bottle is 1/5 of a liter. A liter is 1,000 cubic centimeters, so 1/5 is 200 centimeter.
Okay, so we have 200 centimeter total ink. And we know 1.375 centimeter writes 310 words. We need to figure out how many barrels are in the bottle effectively.
So divide the total volume by the volume per barrel. 200.3755, say 55.
That tells you how many times you can fill the pen. Then multiply that number by 310 words per fill.
Okay, $200 1.3755 is about 145.45. And $145.45 times 310 lower words is around 45,090 words. The problem asks for the nearest 100.
So about 45,100 words. It's a neat little estimation problem using cylinder volume.
It really is. Okay, next up, problem 3 deals with a hollow cylinder, a metal tube open at both ends.
Back to pipes.
Yep. Internal diameter is 11.2 centimeters, so internal radius r is 5.6 centimeters, length h is 21 centimeters, the metal is 0.4 centimeters thick.
Okay, so if the inner radius is 5.6 centimeters and the wall is 0.4 centimeters thick, the outer radius r must be 5.6 plus 0.4 is 6.0 centimeters.
Right, and we need to find the volume of the metal used.
Okay, so we need that formula for the volume of material in a hollow cylinder.
We have all the numbers, R6, R5.6, X21. Plug them in. 5.62 times 2110.
So that's 3 Febonies, $31, $31.36 times 2111, which is pi $4.64 times 2111. Using a Foxfire 26 one again, the result comes out as $306.24 centimeter. The example rounds it slightly to $306 2 centimeters.
Definitely, especially in manufacturing or construction. Okay, problem 4 is more of a visualization thing. You have a rectangular sheet of paper, 22 centimeters by 15 centimeters. What's the volume of the largest cylinder you can make by rolling it along the longer side?
Ah, okay. So you're rolling it so the 22-centimeter edges meet up.
Right, so that 22 centimeter length becomes the circumference of the base.
Exactly. And the other dimension, the 15 centimeters, becomes the height, h of the cylinder.
So circumference $2 R equals 22 centimeters and height 1 over 15.5 centimeters. We can find R from the circumference. $2 times phi times R 22 2.
Yeah, the 22s and the 2 cancel nicely there, leaving 1 rolled per 5 to 2.5 centimeters.
Okay, so radius is 3.5 centimeters, height is 15 centimeters. Now we find the volume. I times 3.5 times 15 tellers. Crunching those numbers gives $577.55 centimeters.
$577.05 centimeters. It's interesting to think if you rolled it the other way along the 15-centimeter side, you'd get a different volume, right? A shorter, fatter cylinder.
Absolutely. You'd get a different radius and height and thus a different volume. It shows how orientation matters in maximizing volume, which is important in things like packaging. Cool. Okay, final worked example. Problem 5. We have a cylindrical vessel, diameter 30 centimeters, so radius 15 centimeters. It's got water in it. You drop a solid metal cube in, and the water level rises by $1 frac centimeters.
One awkward fraction. Let's convert it. $99 times 1 plus 41 is frac centimeter.
Okay, frac centimeter. We need to find the edge length of the cube and its total surface area.
Right. The key principle here is displacement. The volume of the water that got pushed up must be equal to the volume of the submerged object, the cube.
Ah, okay. So we calculate the volume of that slice of water that rose up using the cylinder volume formula.
Exactly. With the vessel's radius 255 centimeters and the water rise 125 centimeters. So volume times 15 times Draxity.
Using frac 7, let's see, times 225 times frac. There must be some nice cancellation here.
There is. The 7 goes into 140, 20 times. The 22 and 99 share a factor of 11, leaving 2 and 9. The 9 goes into 225, 25 times. You're left with $2 times 25 times 25.
Which is 1,000. Exactly 1,000 cubic centimeters.
Right, so the volume of the displaced water is 1,000 centimeters. And therefore, the volume of the cube is also 1,000 centimeters.
Okay. And the volume of a cube is its edge length, let's call it A, cubed. So A3 equals $1,000.
Which means A must be
the cube root of 1,000, which is 10. So the cube has an edge length of 10 centimeters.
Perfect. And the second part was the total surface area of the cube. A cube has 6 square faces, each with area $2.
So $6 times 82, 6 times 100 equals $600 A2.
There you go, 600 centimeters.
Nice.
This one nicely ties together cylinder volume and cube properties via the concept of displacement.
So looking back at all these examples, what does this all mean? It really shows these formulas aren't just, abstract math. They solve actual problems.
Absolutely. For figuring out how much ink you have, to how much metal is in a pipe, to dimensions of objects based on water levels, they're tools for quantifying the physical world.
And the source materials included a whole bunch of other exercises too, right? Just touching on different scenarios.
Yeah, a really wide range. There were straightforward ones like finding volume and surface area given radius and height. Then things like water capacity of pipes, how far a cylinder rolls, cost of plastering a well, which is cylindrical.
I remember seeing ones about recasting metal from one cylinder shape to another, finding dimensions if you only know, say, the curved surface area and diameter,
Right.
Calculating the weight of pipes.
Right, and more displacement problems with different shapes, working out the wet surface area if a cylinder is only partly full, the area of open pipes, comparing cylinders with proportional dimensions.
There was even one about percentage change in volume if you change the radius or height, and figuring out the minimum metal sheet needed for a box, allowing for waste.
Yeah, and determining vessel sizes, comparing rolling paper different ways again, embankment problems around wells, finding inter-outer radii from surface areas and volumes, just a huge variety.
It really covers a lot of ground, shows how fundamental this shape is.
It does. It really drills down into applying those core formulas in lots of different contexts.
Okay, so let's try and summarize the key takeaways from this deep dive.
Well, we started with the basics. A cylinder has that uniform circular cross-section defined by radius r and height h.
And we got the key formulas. Tera-ard for base area, $2 for base area, $2 for circumference, $2 for the curved surface area.
A $2 pi r h plus r for the total surface area, and a $p for the volume of a solid cylinder.
Then we looked at hollow cylinders, bringing in the outer radius r and inner radius r. We saw formulas for thickness, cross-sectional area, inner and outer curved surfaces, total surface area, and importantly, the volume of the material itself.
And the solved problems really hammered home how these formulas are used, calculating dimensions, volumes, capacities, material usage, even using displacement.
Yeah, it provides a really solid foundation, I think, for understanding cylinders and how we measure them.
Definitely, it's a shape that comes up constantly.
Right. So, for a final thought, something for you, the listener, to consider. Just look around you right now, wherever you are. How many cylindrical objects can you spot?
Yeah, cans, bottles, pipes, pillars, maybe even parts of furniture or lamps. They're everywhere when you start looking.
Think about one of them. How might you estimate its volume or its surface area? What kind of practical questions could knowing those numbers help you answer?
It's a good exercise, applying these concepts to the real world around you. You might be surprised how often this kind of geometry is relevant.
Thanks for exploring the deep end with us today.